So let's move to the next topic, which is collectives and non-blocking collectives. And some of you would be familiar at least with the basic collective functions in MPI. So in addition to sends and receives and all the varieties of sends and receives, MPI has a whole set of functions that are defined as collective, where collective means that everyone in the communicator, that is the parameter to that function, must call that function. And they usually specify some kind of communication pattern that is what that operation does. So a common one is MPI broadcast, which takes data from one process that is specified as the root in that call. In that function call, you specify who's the root. It doesn't have to be rank 0. It could be rank 15 or whatever. And the data from that is sent to everyone else in the communicator. Similarly, the MPI reduce also takes data from everyone and combines it at the root with an arithmetic operation. So you can find the min or the max of all the data, and the result is at the root that you specify. And this is useful in applications because you need to do these kinds of things. And instead of you hand coding all this, these algorithms are implemented quite efficiently. So when you call these functions, there's a huge amount of literature on how to optimize collective operations on networks and this and that, and all that a lot of it has been incorporated into MPI implementations. Some of them use hardware methods also to accelerate some of the collectives. So you should use collectives wherever you can and let the implementation do the job. As I said, it's coordinated among processes. There is no tag. So the MPI send and receive have a tag parameter, and tag is one of the things that is used to match a send and a receive. The collectives don't take a tag parameter. You are required to call the collectives in the right order on that communicator. So if processes are doing a broadcast, reduced, and all gather, everyone must call broadcast, reduced, all gather in that order, and they will match each other. And MPI 3 has added non-blocking versions of collectives as well, and we will see that. And collectives can be, there are 3 types, I would say. Synchronization, there is some that do just data movement, and there are some that do data movement with some computation or arithmetic operation on them. So the one that does synchronization only is MPI barrier. And what a barrier does is it guarantees that no process will leave the barrier until every other process in this communicator has reached the barrier. So you may be anywhere in your computation. If one process calls a barrier, it will not get out until everyone has reached, everyone else has called the barrier. So that is the guarantee. But this barrier tends to get abused or used unnecessarily in MPI programs. People tend to just add it just for safety or just to be sure, or I've done a lot of stuff, let me just call a barrier to get things. It's unnecessary synchronization. So you should think twice whether is a barrier really needed here or not, and go ahead and remove it if not. In fact, there are some people who have developed tools that look into your code and try to flag unnecessary barriers in your computation. One place where it is used is if you're doing some kind of timing. If you want to time some portion of your code, then you typically call a barrier so that everyone has reached there, and then you're actually measuring the time taken for this parallel portion of your code. And at the end of that code block, you can again call time, or in some cases, people again call a barrier and then time just to get the maximum time that any process could have taken. So this is just when you're measuring time. But when you're running in production, you could comment out the barrier. Another place where it is used is when you're doing some shared memory stuff, so or RMA in some cases, and you want to really make sure that processes have reached a particular state. that's where you may call a barrier. But in just MPI send, receive, and collectives, you don't need a barrier, because there are other parts of your code where there is some implied synchronization in any case. If you're doing a collective like an all reduce or all to all, where everyone is waiting for the result from someone else, then that is an implied barrier in there. So you don't need to, again, go in and add a barrier. Is this clear? I mean, that barriers are not to be used unless really needed. Okay, so this just shows what a broadcast looks like. And if the root, which could be any rank, this is just as an example, rank 0, has some data. At the end of it, everyone gets that data. Then there is a scatter operation, which is, it takes, I mean, you can think of it this way. The root has an array of data. You want to chop it up into pieces and send the pieces separately to different processes. So if root has A, B, C, D, at the end of the operation, A will remain on the root, but 1 will get B, 2 will get C, and 3 will get D. The way it's specified is in the MPI scatter function is it is just specified in terms of the size of this first element, and then those elements of those size are sent to the different ranks. So B will be sent to rank 1, C will be sent to rank 2, and D to rank 3. And the opposite of scatter is a gather. So MPI gather, what it does is it takes data from the different ranks and then stores them at the root in a concatenated fashion. So collecting pieces from everywhere and storing them concatenated. All these are implemented internally as, using binomial trees or other things. Torsten, there was a figure that Torsten drew here yesterday. So internally, it's implemented efficiently. So the last one was, where was that? The last one was gather, where everyone's data goes to the root. There is another called all gather, where everyone gets everyone's data. So it's not just at the root, but A, B, C, D is now available everywhere. So that's why it's called all gather. But it's the same data. So everyone is contributing some data that goes to everyone else. It's not a distinct, everyone getting different data. The most general, or where it's distinct, is called all to all, where everyone has a distinct data to be sent to others. So here, A0, A1, A2, A3 will go to rank 0, 1, 2, 3, and similarly, B0, 1, 2, 3 will go to rank 0, 1, 2, 3. So everyone has a different data item to be sent to everyone else. This is the most complex pattern to optimize, and it's the most general also, because this can be implemented more efficiently, since in a tree fashion you can send the same data to different processes and so forth. But here, you have to make sure that you're routing the right data to the right process. So this performance of all-to-all is usually the worst among all the collectives. But if you need to use it, you need to use it. And so those collectives just do data movement. They don't do any operation on it. There are reduction functions and scans and others that do some operation on the data. So here, if you do an MPI reduce on this data item, the result will be stored at the root, not as a concatenation in gather. So gather stores it as a bigger array. Here, the result will be stored doing some arithmetic operation on the data. So if MPI sum, if you use MPI sum as the operation, then the result here will be A plus B plus C plus D. Whatever is that value will be the resulting value. And there is an operation called MPI scan, which does, it's also called parallel prefix in some context. It's like a reduction, but each process gets the result only up to its own rank. So rank A will get A, 2 will get A plus B, and 3 will get A plus B plus C, and so forth. So this is a more complex one, but there are some parallel algorithms in the literature that are defined using MPI scan, not MPI scan, but scan as a primitive to build these parallel algorithms. So that's why it's supported. And there is another version called exclusive scan, which you don't get your own contribution. So you will, rank 1 will not see its own contribution in there. It's only of the previous ranks. So all varieties are provided. So as I said, there are many routines. We've seen what are called the regular collectives, where the amount of data that a process communicates to everyone else is the same. But there are other versions which are called the V versions. They take a V at the end, where everyone has a different amount of data to communicate. So if you're doing a gather V, it means that everyone has different amounts of data. They are all being gathered to the root. And the different amounts are again specified as a vector. So there's an array of size, number of processes where you pass that information. These are all versions, and yeah, I think we've covered all this before. Okay, so as I said, for the reductions, they do an arithmetic operation. So what are the allowed arithmetic operations? So there are several that are predefined in MPI. The common ones are predefined. You can build your own as well. So if you want to do something specific that MPI doesn't support, there is a way to define your own function and pass that to MPI, and that will get used as the arithmetic operation. So the common ones are max, min, prod, sum, the logical and logical OR, then the bitwise and bitwise OR, and the max lock and min lock will also tell you the maximum and the location of the maximum. So these are predefined, and there is, as I said, there is a way to create your own operation as well. So you can create your own function and then pass it to MPI op create. You have to specify whether this function is commutative or not. That's just some detailed stuff. And then you can create an MPI op and then use this as, instead of MPI sum, you use this op as the parameter to MPI reduce. So it's just additional flexibility. The more widely used, more commonly used ones are the predefined operations. Okay, any questions so far about collectives? These are all the blocking collectives. They have been there since MPI 1, most of them. So they've been there a long time. And you're probably using them already if you're an MPI user. Let's look at non-blocking collectives. So this is a new feature added in MPI 3. MPI 3 came out exactly 2 years ago, so September 2012. So these should be available in MPitch and in OpenMPI at least, and in some of the vendor implementations. I don't know if they're actually deployed on the Cray at Oak Ridge or the Blue Gene at Argonne yet, but they should be there soon. So the idea is the same as non-blocking point-to-point communication. MPI has had MPI I sends and I receives, and so that this extends that concept to collective communication. What is? Yeah, I think it's that. So it is defined very similarly. So just as the sends have an I before it to make it non-blocking I sends, the collectives are also defined similarly. It's an MPI I bcast or an MPI I reduced, yeah? I stands for immediate. And that's also for some historical reason that in 1993, there might have been some other communication library that used that term for non-blocking. And that's why it ended up being used. So it's the same thing. It also returns a request object, which is the same as in the point-to-point, is the same type of object. And you can use the same kind of test and wait functions for test and wait on completion of the collectives. And the semantics are that the function will return immediately. What that means is when you call an MPI I reduce or I broadcast, that function will return independent of what other processes are doing. It will not block in waiting for something else. Now, how long that might take is up to the what immediately means is up to the implementation. But If you have another process in a long compute loop, this cannot wait for that compute loop to get over and call some other MPI function. The non-blocking has to return right away. That is what that means. And what we mean by no progress guarantee is, when does the collective communication actually happen in this case? Does it happen in the background while you're doing some computation, or does it happen at the beginning or at the end? So that's not specified in the standard. It could happen in the background. It could happen, it could start something in the ISEND, and it's up to the implementation, basically. Or it could defer most of it till you call MPI test or wait, and that could also be a valid implementation. Yeah, so this is again more or less what I covered. What are the restrictions? So again, there are no tags, and the same in-order matching rules exist. So if you're calling an I bcast, I reduce, then on the other ranks also you have to call an I bcast and I reduce in the same order. And some of the collectives, as I said, take a vector parameter, right? The gather V and the scatter V. You're passing an array of counts to that. So when you call the I gather V or I scatter V and you pass that array of counts, you should not change that array of counts until the operation is over, is what this says. And MPI cancel is not supported on collective operations. So MPI has this feature of canceling a communication, which I hope you don't use too much, because it's a bit of a pain to support for the implementation. So you can do an MPI I send and then call MPI cancel, and that's supposed to cancel it if it has not been matched on the other side. And similarly, you can post a MPI I receive and cancel it at some time. Cancel is useful for receive, and the reason it's useful is sometimes in your application you may not know how many receives you're going to get. And it might be a function of data, it might be a function of what someone else is doing. So you might post more receives than are actually going to happen. And when you discover that, you can go ahead and cancel the additional receives so that you can finalize without any pending operations still there, because you're not allowed to call finalize if there are some unmatched I receives, and you might get some error in the finalize. So it's useful in that sense. On the send side, it's less useful. That is, you've sent somebody and then you changed your mind or something like that. So it's provided. You can do that, but for the non-blocking collectives, it's not supported. So MPI cancel will not work for non-blocking collectives. Well, I'll skip that. So there's a non-blocking version of everything. So there's even a non-blocking barrier. So does this even make sense, or what is a non-blocking barrier? Because a barrier says that when I call a barrier, I will not get out of it until everybody else has called a barrier. So if I call a non-blocking barrier, when do I get out, or what does it even mean to get out? So actually, it can be useful, and it is available in other. So UPC, the PGAS language, UPC supports what I think they call it a split phase barrier or something, and the idea here is again to avoid synchronization. So when you call a barrier, regular blocking barrier, you will sit in it until everyone else calls the barrier. And if they are off doing something else, you're stuck in there. So that's a waste of time. So what this says is that it's effectively it's broken into two parts. One is a notify, where when you call the I barrier, that's effectively saying, okay, I have reached the barrier, but I don't quite need to know whether everyone else has reached the barrier right now. So you get out of that. It's an I barrier, so you get out. And at the point where you really need to know that everyone is there, you call your MPI wait. So it's sort of divided into two parts. You're squeezing out more out of you're trying to avoid the synchronization as much as you can. And when you call that MPI test, rather the MPI wait, which completes this I barrier, that will not return until everybody has called their barrier. At least everybody has called their I barrier. They don't have to complete. So the other thing is what is completion of an operation in MPI? So for a send and receive, it's more or less clear. So when an MPI send completes, what it means is the data has been copied out of the user buffer, and you don't know anything more than that. You don't know whether the receive has, it has reached the other side or it's somewhere in the middle, or you don't have that information. All you know is that your send buffer is free to be reused. You can overwrite it, you can free it, you can do whatever you want. In the non-blocking send, what it means is when the non-blocking send returns, you cannot do anything because the operation is not complete. That buffer is still being used for communication. You should not modify it. When you call the wait, that's when the operation is completed locally. Again, you don't know whether it's completed on the other side. On the receive, it's more clear because when you call a receive and you get out, unless you have the data, you're not going to return from the receive. In a collective, what does completion mean? Again, completion is local completion. So MPI broadcast, when it completes, and you're the root, all it means is that the data has been copied from the root's buffer, and it's in the network or somewhere. It doesn't mean that everyone has received it. They will get it, but the root doesn't know that they have actually gotten it. And similarly, on any of the other nodes, when MPI broadcast has completed, all it knows is that it has gotten that data. It doesn't know what the others have, where the others are in that. And it doesn't need to know. In the distributed memory, you typically don't need to know whether somebody else has gotten that data. They will get it. And we'll see more of this in the one-sided communication in the afternoon, where it gets a little more important to know where the communication has completed or not. So again, the split barrier is like a notify, and then at the completion, where you call the test or wait, is when the actual barrier semantics become meaningful out there. Any questions about this? Yeah.
Can you mix blocking and non-blocking barriers?
Not in the same call. So if somebody calls an I barrier, everybody must call an I barrier. And same for the other collectives. Like if somebody calls an I broadcast, everybody must call an I broadcast for that function. Of course, the next function call, you could again switch to a blocking function. Yeah, let me just, but that's a good question, because in the point-to-point communication, you're allowed to mix the two. So you can do a non-blocking send on one side, and it can be matched with a blocking receive on the other side. That is allowed. But in the collectives, you have to maintain that. Yeah.
You mentioned that there is some benefit using a non-blocking barrier. How much benefit are we talking about?
So that's up to your code. The benefit is, can you do useful work yourself at the point where you indicate that, okay, I have reached this barrier stage, and before checking that where you really need to know that others have reached that stage. If you can do useful work in that period, then that's great, because you have not wasted that time.
I mean, but there would be an additional overhead because you are making two calls,
But one of them could be local call. So let's say there is the I barrier, and then you spend a lot of time doing some work. Then that test could be local, and hopefully in the background, MPI has figured out for you that everybody has reached the barrier. Then the call would be quick, because then you already know that the barrier is okay.
Let me rephrase the question. Is it typically used by people? Because
it's a new feature. So
I mean, the reason I say that is, if you are going to call a barrier, you essentially are at a point where you need to know, okay, is everybody there? And
right. So in the distributed memory model of MPI, that is traditionally the way that you call a barrier when. But this is a new feature in MPI 3, and the implementations have just come out. So people have not thought in those terms that in my code, can I actually use this? So you had something else to say, or?
I mean, it's really distributed termination detection. So that the common use is, I'm not ready to finish. So I go off and do stuff, And then at some point I say, okay, well, I'm done with my work, but I may still be needed to respond to stuff that is sent to me. And so, in fact, we were talking about sort of unstructured meshes. If you're in a case where you don't know the communication pattern in advance, then what you might do is, I will send requests for the stuff that I need, then I will call iBarrier, because I am done with what I need, but other people may not be done. I need to find out when everybody is done. Then I will receive as I'm getting requests, and I will test the iBarrier to see if it's complete. When the iBarrier is complete, everybody is done. So it's something like that.
Yes. Thank you.
So we are close to done with this part. We can move to a hands-on. I think this just summarizes. So in general, non-blocking collectives are new, but Torsten, who spoke yesterday, has done work in that, and he has published some papers, and he has shown benefit in some applications of non-blocking. And he was the one who got non-blocking collectives into MPI. He had an initial implementation in a library called NBC lib or something, which is still available. So that's separate from MPI, where you could download and use his non-blocking collectives. But now you can get it directly in MPitch and probably even OpenMPI.